Okay. Hmm. So basically, so let's start from 2. ध्यान করে গেল নাকি? হুম। So we have to show that T has no cyclic vector. Okay. So there exists no, so we have to show that there doesn't exist an alpha such that alpha T square alpha is a basis of R3. Okay. So what should be our approach? So first compute the characteristic polynomial. So you will observe that the CH polynomial is x minus 2 square into x plus 1. Okay. But you clearly see that this is a diagonal matrix. Since T is diagonal, minimal polynomial can't have repeated factors, which implies the minimal polynomial is x minus 2 into x plus 1. Okay. And we have shown that if T has a cyclic vector, then the minimal polynomial is equal to the T annihilator of alpha, right? So if T has a cyclic vector alpha, then the T annihilator of alpha is x minus 2 into x plus 1. Okay. Which is of degree 2 which is less than 3, which is the dimension of R3. Okay, so clearly thus there does not exist any such alpha. Okay, because if you remember, we have shown that, I mean, the degree of the T annihilator has to be equal to the dimension of the subspace, right? This was, I think, yes. The degree of P alpha is equal to the cyclic subspace Z alpha T. In this, and if T is cyclic, T has a cyclic vector, then V is this. So the degree of the P alpha has to be dimension of V, and we have shown that this P alpha turns out to be the minimal polynomial of T. Okay. Now next, so if alpha is minus 1 comma 1 comma 3 and T is 200 02000 minus 1, you can compute T alpha is like this, and T square alpha is like this. Okay. And see that this is nothing but 2 minus 1 3 plus 2 minus 2 minus 3. So clearly T square alpha is linearly dependent on these two, alpha and T alpha. So Z alpha T is spanned by alpha and T alpha. Okay. Okay. So let's move on to the next problem. So we will have to find out the T annihilator subspaces for these two vectors. Okay. First, let's find out the characteristic polynomial. So the CH polynomial as I can see is 1 minus x I0 minus 1 2 minus x minus I 0, 1, 1 minus x, right? So this will be x cube plus 4x square plus 2i plus 5x minus 2i plus 2. Now if alpha equals to 100, then what is T alpha? T alpha has to be the first column, right? What is T square alpha? It is, according to my calculation, this becomes minus 3, 1. Okay. Now we will check that whether they are linearly independent or not. So take a linear combination A alpha plus B T alpha plus C T square alpha equals to 0. So we get A 100 plus B 1 minus 10 plus C 1 minus I minus 3 minus 1 is 000. So you get three equations. One is A plus B plus C minus Ci equals to 0. This is one. Another is minus B minus 3C equals to 0. The other is minus C equals to 0. Okay. See, minus C equals to 0, so C equals to 0. Put C equals to 0 here to get B equals to 0. Now C and B equals to 0 implies A equals to 0. Okay. So this implies A equals to, this implies A equals to B equals to C equals to 0, which implies alpha, T square alpha are linearly independent. Okay. Thus, alpha is a cyclic vector. Okay. Okay, so I will give you 3-4 minutes to try 4. Try 4. Okay. So I will give you 3-4 minutes. Please try 4. Okay, so let's do number 4. So let's write down the definition of Z alpha t square first. What was it? Like g t square alpha, all those polynomials in t such that gx belongs to kx, right? Okay. And we have that Z alpha t square is V. Okay. Now what is Z alpha t? This is nothing but g t alpha such that gx belongs to kx, right? But you see one thing, x square belongs to kx, right? This implies x square, I mean you are acting x square on t of alpha, which is t square alpha is also in Z alpha t, right? This implies g t square alpha belongs to, I mean what I am trying to say is that if t square alpha is here, then Z alpha t square is a subset of Z alpha t, na? So this is V, so this is also V, because this is the whole space. So alpha is a t cyclic vector. Okay. Now what about the converse? Converse counter example, I mean the converse is not true. So if you take t is, see this is the standard trick, okay? I mean this is a very standard trick. Suppose, I mean, okay, so first let's write down the example, then I will explain the trick actually. So t alpha is 0 1, so clearly alpha t alpha is R2, the span. So t has a cyclic vector alpha, right? But t square alpha is 0 because t is nilpotent. This implies Z alpha t square is only generated by alpha. Okay, so no, I mean let's write it this way, that see we have taken a, I mean the trick, you see the trick, the t square is 0, so 0 operator can't have a cyclic vector, na? So t square does not have, so that is the trick, you take t such that t square is 0, does not have a cyclic vector. Okay, let's do 5. This is a problem we have done a lot of times, but okay, let's do it again. So n is an nilpotent matrix on an n-dimensional vector space, and alpha in to the power n minus 1 alpha is not 0. So clearly we will have to show that this set is linearly independent. Okay, so take a linear combination 0. Now apply n to the power n minus 1 on both the sides, you get the rest of the terms are 0 now, because here the power of n is greater than n. This implies n is 0 is 0 because this is non-zero. So you put a0 here, I mean you put a0 equals to 0 here. Now the equation boils down to this. Okay, now apply n to the power n minus 2. Now you get this imply a1 is 0, and doing this way you will get a0 equals to a1 equals to n minus 1 is 0. So this is linearly independent. Okay, this is a linearly independent set of length n. So z alpha n is v because it has dimension n. Okay, and what is the matrix of n with respect to this basis? We know that n alpha, like 0 into alpha plus 1 into n alpha, n square alpha is 0 into alpha plus 1 into n alpha plus 1 into n square alpha. So this way you will get a matrix like this, right? Okay, so again I will give you a few minutes to try 6. Just let me check cyclic decomposition and rational form. This is 7.2. Just a minute. Cyclic decomposition, rational form, Jordan form. I believe I will have to skip the proof, because I mean in the next class, because the cyclic decomposition, the proof is very long. It is extremely long. Yes, the Jordan form is here, but we won't be able to skip the previous chapter. We will have to do it. Okay. Okay, so let's try 6 now. The next chapter is easier. Metric, I mean, inner product spaces is it's easier. I read the whole book all by myself. Only chapter 6 and 7 I was taught by one of my professors. Okay, so try 6. We are 45 minutes. Try 6. So let's do number 6. So we will have to give a direct proof that suppose given a polynomial we have a companion matrix. So we will have to show that this is the characteristic polynomial is the same polynomial. Okay. So first let p equals to px be like a naught plus a1 x to the a1 x up to x to a n minus 1 x to the power n minus 1 plus a n sorry. So what is the companion matrix? We know that we will just have to write down the coefficients in this order, and then 1 in the lower diagonal. That's it. Okay, 0 everywhere else. So let's try to compute the characteristic polynomial for this. So let's try to compute xi minus a determinant. Okay, so what will be that? So x 0 0 0 plus a naught, I mean only a naught. So every sign will change, a1 up to an minus 1, this, right? Okay, sorry, I will have to write x here. Okay, now I am doing a transformation. Okay, so do this. So write r1 prime equals to r1 plus r2x up to rn x to the power n minus 1. So tell me, what do you get? So you are replacing row 1 by this, right? So first tell me what is r1. What is this term? I mean, so what is row 1? Row 1 is like x a naught, right? Now what is r2x? R2x is x times 1 x 0 0 0 a1, right? X to the power n minus 1 times 0 0 0 1 x plus a n minus 1, right? So what do you get? In the first you get like x up to a naught. In the second you get x square, then 0. In the last column you get 0 0 0 x to the power n minus 1 here, and x to the power n plus x to the power n minus 1 into a n minus 1 in the last column, right? If you add all of them, what do you get? Wait a minute, am I doing it right? Just a minute. R1 is that, so there was like E1, right? So here we will have an A1x. Wait a minute. So I think I have done some miscalculation. Just a minute. -2 is here, so that will be. Now it's okay. Now it makes sense. So you see this x and the next x will be cancelled out, okay? So this x square will be cancelled out with the next x square. So you will get this matrix. A naught plus A1x up to an minus 1 x to the power x to the power n 0 0 0, I mean minus 1 0 E1 plus A2x up to x to the power n minus 1 and so on, okay? 0 0 0 minus 1 x plus an minus 1, okay? So you take px common from the first row, okay? So you get this, or maybe you can do one thing. I mean, if you expand this determinant with respect to the last column, expand with respect to the last column, what do you get? You see, you get this, you get px and then you get this last column. So this will be cancelled out, only this matrix will remain like the cofactor, okay? So you basically get minus 1 to the power n minus 1 into px, okay? Which is, so I mean this is nothing but this means px na. Wait a minute. Oh, no. You will get this n minus 1. I mean, you will get it here. Sorry. This is px. Okay. So that's problem number 6 done. Okay. Try problem 7 for a few minutes. Then we will do problem 7 and then problem 8. Try problem 7 for again 3-4 minutes. E- So M be an n-dimensional vector space. T linear operator and T is diagonalizable. If T has a cyclic vector, then T has n distinct characteristic values, and if T has n distinct characteristic values, and if alpha 1 to alpha n is the basis of the characteristic vector, basis of characteristic vectors for T, then this one, I mean summation of all those eigenvectors is a cyclic vector for T. Okay, let's see. So A, okay. Suppose alpha is C1 to Cn, be a let each vector. So call it beta. No, I mean, so if since T is diagonalizable, I mean some ordered basis beta with respect to some ordered basis beta, T beta is like. So T alpha, you will see that T alpha is like lambda 1 C1, lambda n Cn. You apply T on it, and you will realize T to the power I alpha is basically. Okay. Now think about this matrix like alpha, T to the power n minus 1 alpha. How does this matrix look like? C1 to Cn, then lambda 1 C1 up to lambda n Cn, and lambda 1 to the power n minus 1 C1 up to lambda n to the power n minus 1. Now you see one thing, okay, if lambda I equals to lambda j for some I not equal to j, then we get ith and jth row equal of this matrix, right? Right? So call it A, equal in A, which means A is singular, right? But we all know that since alpha is a cyclic vector, we know that this is a linearly independent set, right? So this set is linearly independent. So here is a contradiction, right? So lambda I can't be lambda j. So T has every eigenvector to be distinct. Okay. There is an alternative method to prove A as well. Alternative method. So what do? We basically take let T has k distinct eigenvector. Okay. Each values C1 to Ck. Since T is diagonalizable, what will be the minimal polynomial? Product of these factors, right? But if T has a cyclic vector, since T has a cyclic vector alpha, Px is the T annihilator of alpha, and dimension of Z alpha T, since this is V, this is dimension of V, this has to be equal to what? Degree Px, right? Which is K. So you see, dimension V is K. This means T has to have, this means K equals to N basically. Okay. Since this is N. Okay, now let's move on to B. So this is a characteristic vector, and we have to show that this is a cyclic vector. Okay, let's see. So alpha is summation alpha I. So T alpha is summation I running from 1 to n Ci alpha I. Okay. And you know very well that you apply T to the power j in alpha, so you get summation like summation I running from 1 to n T to the power j alpha I, and which will be nothing but when Ci to the power j alpha. Okay. And these eigenvalues are given to be distinct, no? In distinct characteristic values. So no Ci is equal to Cj. So Ci is not equal to Cj if I not equals to J. So now we will have to check that whether this linear combination is 0 or not. So take a linear combination. Lambda alpha I plus lambda 1 summation Ci alpha I, okay, up to lambda n minus 1 like summation Ci alpha I. Okay, so take, you get this like lambda naught plus lambda 1 c1 up to lambda n minus 1 cn minus 1 times alpha naught lambda 1 plus lambda 1 c2 up to lambda n minus 1 sorry lambda 1 c1 plus lambda n minus 1 c2 to the power n minus 1 alpha 1 and so on. Lastly you get lambda n cn plus lambda n minus 1 cn to the power n minus 1, this, right? Now alpha is a linearly independent, right? So all of these are 0, so you get lambda naught plus lambda 1 ci plus lambda n minus 1 ci to the power n minus 1 is 0 for 1 less than equals to I less than equals to n, right? Now this means that the polynomial lambda naught plus lambda 1x up to lambda n minus 1 x minus 1 has n distinct roots, because every ci is a root, distinct root, but this is an n minus 1 degree polynomial, right? This means this is a 0 polynomial, so lambda 1 equals to lambda 0. Okay, so they are all linearly independent. So let's do 8 and that will be it for today's class. let T be the linear operator on a finite dimensional vector space V. Suppose T has a cyclic vector. Prove that if U is any linear operator which commutes with T, then U is a polynomial at T. Okay. So we have given that there exists alpha belongs to V such that Z alpha T is V. Okay. And beta is a basis, which is the cyclic basis. I mean dimension V is taken to be n here. So U alpha, what is U alpha? I mean U alpha is again a linear combination of all this C1 T alpha Cn minus 1 T to the power n minus 1 alpha, right? Now consider the polynomial fx with these coefficients, c1 I mean c0 plus c1x up to cn minus 1 x to the power n minus 1. Our claim is u equals to f of t. Okay. Now we clearly from this line we are seeing that I mean we have u alpha is clearly ft alpha. Okay, from this line we have it. So like u commutes with t. Okay, so u commutes with every power of t. So write u t to the power I alpha. This is nothing but u alpha, which is again t to the power I f t alpha, which is f t to the power I alpha, right? Now you see that. So I mean what I am trying to say is that u I mean uv, so what should I say, uv is ft of v for all v belongs to this set, right? But this is a basis, na? This is a basis. So uv equals to ftv for all v belongs to capital V. Because for every basis element, if acting I mean if implying I mean applying u means basically applying ft, so uv is ftv for all v belongs to capital V, right? Which means u is ft. Okay, so that's it for today. I will have to plan a bit for the next next Thursday. I mean, okay, so let's see. I mean, I don't think we can cover the whole proof of cyclic decomposition because that's too long. That's way too long. It will take probably 2 classes only for the proof.